Hi guys, my name is Samuel Jasper from CSE department, currently in my first year. My topic for Tech Talk in matrices and calculus is weakly filtered matrices. Introduction to weakly filtered matrices. A weakly filtered matrix is a mathematically construct typically studied in context of algebraic structures, category theory, or matrix theory. The concept often arises in specialized areas such as representation theory, homological algebra, or in generalizing certain matrix classes. Here is an exact explanation depending on the context. General meaning. In general, a weakly filtered matrix refers to a matrix that satisfies a relaxed versions of filtering process and condition. A filtering condition often implies that rows, columns, or submatrices exhibit some type of hierarchical or partial order structures, but in weakly filter case, these conditions are pretty loosened. Representation of weakly filter matters. A weakly filter structure could relate in representation theory. A weakly filtered structure could relate to a filtration of a module or a vector space where associated matrices represent some weak order between subspaces. For example, entries might satisfy specific inequalities or inclusion relation. In matrix theory, a weakly filtered matrix might be used to generalize block matrices or triangular forms where the conditions on zero entries or constants on off-diagonal elements are less strict. Why to study weakly filter matrices? The study of weakly filter matrices is motivated by their applications and theoretical significance in various fields. Here are some reasons why researchers and mathematicians might study them for better future. Generalizing existing structures, applications in representation theory, algorithm design and computation, applications in data science and networks, conditions to partial orders. Distinguishing characteristics. The main distinction is the deviation from strict patterns found in more conventional matrix structure, like example triangular matrices and many more. Broad applicability. They can represent systems with partial or incomplete orderings, making them more applicable with practical and theoretical settings. Structural generalization. They generalize the idea of filtration, offering a framework for studying broader classes of matrices or algebraic structures. Key features of weakly filtered matrices. Number one, potential for block or submatrix structure. Weakly filtered matrices often have a block or layered structure where each block satisfies certain conditions, but relationships between blocks are more loosely defined. This makes them applicable in modular systems or representation of objects with substructures. Number two, link to filtration in models or spaces. Weakly filter matrices are often associated with filtrations in vector space or models. The matrix represents transition or interactions between layers of filtration, with weak filtering indicating flexibility in how these layers interact. Comparison of matrices. Let's compare some few types of matrices with weakly filtered matrices. Sparse matrix and weakly filtered matrix. Sparse matrix focuses on the presence of zeros, while weakly filtered matrices emphasize weak hierarchies. Dense matrix versus weakly filtered. Dense matrices lack structural constraints, whereas weakly filtered matrices impose relaxed order or relationships. Filtered versus weakly filtered. Weakly filtered matrices are more flexible and general than strictly filtered matrices. Triangular versus weakly filtered. Weakly filtered matrices generalize triangular matrices by relaxing the strict zero pattern rules. Block versus weakly filtered. Block matrices focus on partitioning, while weakly filtered matrices deal with weak order or filtering constants. The formulas for weakly filtered matrices are a and the conditions for weakly filter matrices. Matrix A is equal to A of I and J is a member of row n into n and column R n into n is said to be a weakly filtered if it satisfies certain relaxed constants based on the filtration or partial order. These constants can be expressed as in two types: weakly hierarchical and partial ordering of entries. In weakly hierarchical constants, for indices like I and J satisfying J greater than I, the entries of A may satisfy Aij is greater than or less than less than or is A of I and J is greater than or equal to 0, or modulus of AI and J is less than or equal to function of I and J, where function of I and J is a bound of function defining the relaxation. Number two, partial ordering of entries. If the rows or columns of A correspond to a partially ordered set of P and also greater than or equal to, then A of I and J is not equal to 0, and also J is greater than or equal to I. However, these conditions are not strict. Exceptions might be is allowed. Let's This is one more and we have one more subtopic in a weekly filter matrices, relation to filtration of spaces. If A represents a linear map in a filtered vector space, then V is equal to V1 is a superset or and equal to V2, and V2 is superset and at the same time it's equal to V3 and so on up to Vn. Then A is weakly filtered if A multiplied with a Vi is subset and equal to Vj. For some, j is greater than or equal to I, but this inclusion may fail for some ij or all approximately. Matrix inequalities. In optimization or numerical contents, weakly filter matrices may satisfy inequalities like A is less than or equal to B or A is similar to B, where B is a strictly filtered matrix and the comparison is element wise or a norm. Highlight specific operation. Example, addition and multiplication. In addition, we have an operation. If A and B are weakly filtered matrices of the same size, their sum C is equal to A plus B is also typically weakly filtered, providing providing the filtering conditions are preserved. What are the properties? There are two properties: entry-wise constants and weakly hierarchy or partial order. In entry-wise conditions, if A and B satisfy weak constants like modulus of Aij and modulus of Bij is less than or equal to function of I and j. Then modulus of Cij is equal to modulus of Aij plus Bij less than or equal to modulus of Aij plus modulus of Bij less than or equal to 2 multiplied with function of I and j. Hierarchy of partial order. Weak filtering conditions may still hold if both matrices respect a partial ordering. However, deviation could rise where I and j is equal to 0, Bij is not equal to 0, and at the same time Zij is not equal to 0. This could break the filtering depending on the strictness of the definition. If A and B are weakly upper triangular, a is equal to A level B12 0 and so on. B is equal to B level B12 E 0 B22 B23 and so on. When we add these two matrices, we get A level plus B level, A12 plus B12 E 0, A22 plus B22, A23 plus B23 A23, A33 plus B33. C remains weakly filtered if deviations of E are very small. Matrix multiplication operation. If A and B are weakly filtered matrices, their product C is equal to A multiplied B is generally weakly filtered if the filtering conditions are compatible. Properties. Structure preservation. If A and B are weakly upper triangular, their product is also weakly upper triangular. If for I greater than J, most terms AIK and KJ vanish due to filtering, but small deviation may appear depending on the relaxation approximation. If we represent small deviations in A and B, the error can propagate C equal to A strict multiplied with B strict plus delta. Well, delta accumulate deviation. Example, for weakly upper triangular matrices, A represents A level, B12, 0, and so on. And also B represents B level, B12, B13, and so on. When we multiply A matrix and matrices with each other, we get A level, B12, B level, A level, B12 plus A12, B12, and A level, B13 plus A12, B23, 0, 0, 0, and so on. Applications of weakly filter matrices. Number one, signal processing. Weakly filter matrices model filters with approximate order constants useful in designing systems where strict filtering is impractical due to noise or system complexity. In wavelet of Fourier transforms, weakly filter matrices approximate in transitions between resolution levels. Economics and decision sciences. In decision making processes of economic models with partially ordered preferences or rankings, weekly filter matrices model transitions or dependencies. Input and output models represent interactions between economic sectors where strict hierarchies, example, dependence between sectors are weakly defined or perpetuated. Let's look one of the examples for weakly filter matrices, where A stands Ray represents a matrices 3, 5, 2, 1, 0, 4, 6, 3, E 0, 2, 7, 0, E 0, 8. Adding another weakly filter matrix is B. Example, B is a matrix which represents 2, 1, 3, 4, 0, 3, 2, 1, is 0, 1, 2, 0, 0, 0, 5. When we add B matrices to matrix A, uh, when we add 2 with 3, we get 5. At the same time, when we add 5 with 1, we get 6. At the same time, when we add 2 plus 3, we get 7, and so on. When we get the product C when we add the matrices A and B. This result remains weakly filtered with deviations to E in similar positions. The same example is applicable in uh, for multiplication too. Computational challenges, structure preservation. Operations such as addition, multiplication, and inversion may cause the matrix to lose its weak filtering properties as small deviation small deviation epsilon can accumulate or propagate. When multiplying two weakly filtered matrices, deviation from strict filtering may applying, resulting in a matrix that is no longer weakly filtered. Deviation management. Ensuring that the deviation epsilon remain small enough to preserve the approximate structure while performing computation. Accumulated deviations can lead to incorrect approximations, especially in iterative algorithms. Example, iterative solver or optimization. The future. The future of weakly filter matrices lies in their ability to balance flexibility with structure constants, allowing them to model complex systems with partial ordering and approximate relationships. With advancement in computational power, numerical methods, and application-specific needs, weakly filtered matrices will become increasingly important in diverse fields from quantum computing to machine learning, bioinformatics, and economic modeling. Their robustness in handling uncertainty and scalability in large systems will drive their adoption in both theoretical research and also in real-time world applications. Coming to conclusion, weakly filter matrices represent a powerful tool for addressing complex systems where structural constants may not be realistic or necessary. Their flexible nature, which allows for small deviations from a fully filtered structure, makes them highly relevant in a variety of fields that require approximations, large-scale computations, and real-world modeling. Despite their potential, working with a weakly filtered matrices represents several challenges, including ensuring numerical stability, managing deviations, and developing algorithms that preserve their structure during matrix operation. These challenges, however, are not insurmountable and will likely drive the development of more sophisticated algorithms and computational techniques tailored to weakly filtered structures. Thank you for watching.